Welcome to the NHERI SimCenter's Live Expert Tips, where we feature the capabilities of SimCenter Tools through compelling examples and use cases in natural hazard engineering simulations. In this session, we will introduce you to seismic response estimation with surrogate models using quoFEM. Our expert today is Mia Lochhead. Mia is a PhD student at Stanford University in the Structural Engineering and Mechanics program. Her research focuses on using computational tools such as surrogate models to study the seismic performance of the built environment at the regional scale. Her research aims to explore how high-fidelity regional simulations can guide engineering decisions and enhance community resilience to natural hazards. She holds a BS in civil engineering from the University of Notre Dame and an MS in structural engineering from Stanford University. Welcome, Mia. Thank you for being here.
Thank you so much for the introduction, Sangri. I'm happy to be here. As she said, I'm going to be talking today about seismic response estimation using surrogate models in quoFEM. I know surrogate models are kind of increasingly used and talked about in the field of earthquake engineering right now. And so today I want to give a little bit of an introduction and then talk about my use case for these models. So just to go over today's agenda, we're going to be starting with surrogate models in performance-based earthquake engineering as kind of an introduction. I'll be going then into my application, which is regional assessment of highway bridge structures. And then at the end, I'll do just a short tutorial on using one specific surrogate model in the quoFEM tool. And so with that, let's get started. So before I jump into surrogate models for seismic response estimation, I want to talk about how do we evaluate the seismic performance of a structure to begin with. And so given a structural model and a specified seismic hazard, how do we typically get to structural performance under a given hazard? And in the case of this high fidelity modeling, this typically involves nonlinear analysis of a structure. And so using an OpenSeas model or another physics and structural analysis based model, we can map from both the seismic hazard and the structure to structural performance under a given hazard. And so this is great because it provides us this really detailed high fidelity understanding of what's happening in these models. But the picture changes a little bit if we put this in the context of regional analysis. And so if we're, instead of looking at a single structure, looking at a whole region of structures, these nonlinear analyses really are useful in that they provide really specific results, but this quickly becomes very computationally expensive, which becomes somewhat limiting in the context of regional analysis. And so, of course, there is an alternative to this. We don't have to use nonlinear analysis in a region. And what this typically looks like at the regional scale is using generalized fragility functions. So a methodology like HAZIS or otherwise that maps directly from earthquake intensity to probability of a given damage state. And so these fragility functions are somewhat generalized because they're a kind of specified amount of them that certain structures are sorted into. So there are these kind of categorical definitions of structures that we use in this sort of generalized fragility function method. And so what that means is that although this solves our problem in that it's computationally very inexpensive, it provides somewhat generalized results. And so not nearly as much detail as this kind of high fidelity nonlinear analysis. And so today I'm going to be talking about option 3, which is surrogate models. And so surrogate models can be used in place of structural models. And instead of relying on physics and structural analysis, surrogate models rely on statistics and learn relationships between input and output variables. And so when we kind of abstract this at a broader level, if we have some kind of computationally expensive analysis, in my case, this is nonlinear time history analysis, but this could be a different portion of the performance-based earthquake engineering framework. We could use surrogates to compute downtime or transportation traffic analysis and a lot more. So we have some kind of computationally expensive analysis, and then as an alternative, we have surrogate models. And so surrogate models, kind of at the most general sense, are models that stand in for more complex simulations that can provide more efficient predictions with some level of acceptable accuracy. And there are a lot of different types of these kinds of surrogate models. In no means will this presentation be comprehensive. I'm going to be talking mostly about one specific type of surrogate model. And so that kind of concludes this introduction to surrogate models in performance-based earthquake engineering. And next, I'll be moving on to discuss an application to regional assessment of highway bridge structures. And so this is the use case I've been working on recently, and I think provides an interesting look at using these surrogate models in context. And so here I'm showing a map of the San Francisco Bay Area, and each of these blue points is an individual highway bridge structure. And so the overall goal of this study is to assess seismic performance of a regional bridge stock under an earthquake scenario. So basically, given an earthquake in the Bay Area, what are we expecting our performance to be at each of these individual bridge structures? And so before we jump kind of straight to surrogate models, I think there are a few important questions to think about before we get to that point. So first of all, why would we want to estimate the detailed seismic performance of all of these bridge structures in a region? We already have tools to assess these types of structures using a methodology like HASIS. So we should have a reason of why we want to go farther and have this really detailed understanding of seismic performance. And I think there are a few reasons why understanding this could be important in the context of highway bridges. First of all, it provides us a much more accurate understanding of bridge damage. And thus, if we have a more accurate estimation of bridge damage, that transfers to a more accurate understanding of traffic and economic impacts of an earthquake. Furthermore, the kind of detail that we can get out of these models is providing helpful information for decision support for retrofit allocation, and could be helpful in post-earthquake response planning and just overall provide us a better understanding of seismic risk in a community. And so looking at that, there are a lot of reasons why it might be helpful to have this detailed understanding of seismic performance of these bridges in this region. The next question that we can ask in relation to this is a surrogate model even appropriate in this context? And so in thinking about this, we were thinking that highway bridges are a really common structure. As you can see in this map, these are all over the Bay Area, and they're a really key part of our infrastructure, particularly in this post-earthquake response phase. Furthermore, the design of highway bridge structures is relatively consistent compared to other bridge structures. And because of the quantity of these, the high fidelity models for these bridges for use in the region is computationally unfeasible. And so these three kind of points lead us to deciding that perhaps a surrogate model is appropriate in this context of highway bridges. Finally, third, if we are to use a surrogate model in this context, what are we expecting from it? What are our requirements of our surrogate model? And so in the context of a regional level earthquake analysis, our surrogate model has to be sensitive to both structural changes. So if we have one bridge from 1960 and one bridge from 1990, those likely are going to behave differently. Sensitive to ground motion information. So if shaking intensity is higher at one site than another site, it should be able to pick that up. And then finally, because of those two things, we must be sensitive to structural response information as well. And so given those three different parameters, how do we go about creating a kind of structure-specific, site-specific surrogate model? And so based on those three things that we just discussed, we first need to think about structural design and modeling parameters. So this is how we pick up the variability in the bridge structure itself. Second, we need to have ground motion parameters, which pick up the variability in the ground motion. And then finally, we need to have these output structural response parameters. So this is given a specific structural design and a specific ground motion, how are we expecting our bridge to behave? In light of these three kind of different forms of variability, we can ask two questions in this performance-based earthquake engineering framework. The first is, at what earthquake intensity does each bridge structure collapse? So what is our expected collapse behavior? And we're going to create one surrogate that particularly looks into that question. And then second, given that the bridge doesn't collapse, what are we expecting from our bridge response? So if this isn't collapsing, what are we expecting out of column curvature, forms of damage, et cetera? And so we're going to form a second surrogate that looks into that particular question. So in order to develop these surrogates, we need to decide what are going to be our input parameters and what are going to be our output parameters. And this looks slightly different in these two cases. And this really gets back to these three kind of characteristics on the left that we want our surrogate model to pick up. So in our input space, both in the collapse and non-collapse surrogate models, we have structural parameters. And so this includes things like pier slenderness, axial load ratio, et cetera. And this really gets at the specific structure that we're interrogating. Second, we also have ground motion parameters. And so this really, again, picks up what's the ground motion at our site, what are we trying to predict for? And then as outputs in each of these surrogate models, we have response quantities. And so this looks a little bit different in the collapse versus non-collapse case, but this really gets at what is our expected performance of our bridge given these input parameters. So in order to develop surrogate models that have those inputs and outputs, we need training data. And so in this case, training data is based on high fidelity models that we can use to map from ground motion and structural parameters to response quantities. And we do this by selecting different ground motions. So we select a grid of ground motions that we're aiming to kind of cover the seismicity across California. So we're looking at variable frequency content and variable duration in order to be reflective of the types of different seismicity that we could see across the state. Once we've kind of selected those ground motions to cover that input space in the ground motion dimension, we further select bridge models. And so these bridge models were sampled to be reflective of Caltrans highway bridges, in particular focusing on two-span, one-column highway bridges that were before 1971. And so we pair these ground motions, which are reflective of the seismicity across California, with these set of bridge models that are reflective of the structural designs across Caltrans bridge, the bridge shock. And so once we have these pairings, we can scale up using incremental dynamic analysis up to bridge collapse in order to generate training data. And from this process, we've extracted 14,000 training samples where we can extract collapse information. So at what intensity does each bridge structure collapse, as well as non-collapse engineering demand parameter information. So given that the bridge doesn't collapse, what is our detailed structural response? So once we have this training data, we can start to think about what are the surrogate models we want to use to map from these inputs to these outputs. And as part of this project, I've looked at 3 different surrogate models. The first being multivariate log linear regression, the second being Gaussian process regression, and the third being probabilistic learning on manifolds. I want to briefly point out that there's a live expert tips from a couple years ago from Sangri who that looks at Gaussian process regression in detail. And so because of that, the focus of the rest of today's talk is going to be on probabilistic learning on manifolds, which is the third surrogate model that I've been using in this study. So what is probabilistic learning on manifolds? This model is basically given an initial data set. This model generates a learned data set of additional realizations that preserve the original data structure and comply with user-defined constraints. So what does that mean? Basically, that means that given the black points in this plot shown on the left, this model kind of learns the data structure behind those points and can generate additional realizations shown in blue here. And so basically, probabilistic learning in this title just implies that we're not making deterministic predictions. Instead, we're providing probability distributions of input and output variables. And manifolds just implies that these are geometric flexible structures that can capture the geometry of the data. I'll be referring to this model throughout the rest of this presentation as PLoM, which is the acronym shown here. So there are a couple different characteristics in this PLoM model that's kind of set it apart from other surrogate models. And the first has to do with this input and output variables as distributions. And I'm going to kind of set this up as a comparison to other surrogate models. So in the case of linear regression, we take a single point in the input space, we sample our linear regression, and we get a single point in the output space. So basically, we have input and output points. In the case of Gaussian process modeling, we can sample a single point in our input space and get a distribution as our output variable. So a Gaussian distribution for a single point in the input space. And so this is where PLoM is a little bit different than these initial 2 models. PLoM, on the other hand, samples actually a whole distribution in the input space and generates a whole distribution in the output space. So this idea of input distributions is quite different. And furthermore, PLoM isn't limited to Gaussian distributions. This can pick up all sorts of distributions in the input and output data. And so this is kind of a main departure from some other surrogate models and the way those are set up. This actually lends itself quite well to regional level analysis. So if we are looking at evaluating structures at the regional level, we have ground motions for a given site, and there's variability in those ground motions. So at a given site at SA at 1 second, we're going to have variability in what that looks like at that site. So that means that we are going to have a distribution in our input space, which is earthquake intensity. Similarly, we could have uncertainty in our bridge inventory or material variability within a known bridge design, which also means that we have distributions in these bridge input parameters. And so what this means is that PLoM can actually automatically handle these input variable distributions quite well. The other characteristic that I want to mention about PLoM that kind of is different than other surrogate models is that it implicitly captures correlation in output variables. And so since the data is kind of generated as additional realizations in the space, PLoM is automatically capturing these correlations. And so this becomes really significant for loss analysis. So for example, in the case of a building, if we can have correlation successfully captured between different stories in terms of peak floor acceleration or interstory drift, that's going to allow us to have a lot better understanding of the building performance for something like a loss analysis. And so now that we've kind of covered these two main differences between PLoM and some other surrogate models, I want to kind of walk you through the process of what exactly the PLoM model is doing to make a prediction. And so we start with target data. And so this data is not related to the PLoM model. This is basically just data that represents what we want to predict for. So the target data is a single bridge design with a specific earthquake return period or scenario. And so the green data here just contains our inputs. So this is our structural parameters and our ground motion parameters. And as I mentioned, these are in the form of distributions. So this isn't a single point in the input space. These are distributions in the input space. Second, we have unfiltered training data. And so this blue data represents data across many different bridge designs and many possible earthquakes. And so this is very generalized. This is the data set that I mentioned previously in terms of training data. And so this data, because it's our training data, contains both the inputs and the output parameters. So it also contains those 6 response quantities in the case of the non-collapse surrogate. PLoM, the way we're using it, it doesn't have to be used like this, is set up in 2 separate steps. The first being the step of filtering. So for each of our input dimensions, we're cutting the training data to be within 3 standard deviations of the target mean. And so that in that step, we're using this green target to sample our training data down to data that's more closely related to the area we're interested in. And then the second step in this PLoM model setup is the step of constraining. And this is where the PLoM model really gets put into use. Basically, for all of our input dimensions, we are constraining the PLoM model to match the mean of our input parameters. And so this gets at that blue and black data sampling that I was talking about before, where we're generating additional realizations of this data. And ultimately, this yellow PLoM prediction is going to have both inputs and outputs. So not only do we have our structural and ground motion parameters, this also is providing predictions of response quantities. And so this is the overall workflow of using the PLoM model. And this process of constraining, which is the last step in this process, is controlled by model hyperparameters. So our 2 model hyperparameters are epsilon dB and epsilon k. And I'm going to just give a brief intro to those hyperparameters. So the way this data is set up, we have kind of ranging data from low intensity earthquakes to high intensity earthquakes. And what we're finding is that at low intensity earthquakes, our bridge is performing elastically. And because of that, there's not a huge amount of variability in what our output data looks like. On the other hand, at high earthquake intensities, our bridge is performing inelastically. And because of that, there's a lot of variability in what our model, or what our data rather, is actually looking like. And so this means that these correlations and the data behavior at the low intensity earthquakes versus the high intensity earthquakes is quite different. And so what that means is that since these hyperparameters capture the nonlinear correlation, our optimal values for these 2 hyperparameters actually depend on earthquake intensity. And so at a low intensity earthquake, these hyperparameters look different than what they should look like at high intensity earthquakes. And in order to kind of overcome this, we've developed these hyperparameter functions, which are basically, instead of having a constant hyperparameter, we have this mapping that goes from earthquake intensity up to each of these hyperparameters for both our non-collapse and our collapse surrogate, which helps to address this kind of changing nature of the data structure at low versus high intensity earthquakes. So once we actually have this trained PLoM model, which involves our training data, which can be used to partition, and our optimal functions for our 2 hyperparameters, we can start to ask the question, is our model sufficiently accurate for use? Which is somewhat of a complicated question, but we've gone about trying to answer this by sampling 3 different sites across the state of California and 3 different bridge structures with different different input parameters, and pairing each of those for a total of kind of 9 pairs of site and bridge, and evaluating each of those at 6 different earthquake return periods. And so basically, we've assembled these kind of 3 sites, 3 bridges, and 6 return periods as a validation study of this model, where we're using independent suites of analysis data for each bridge site intensity pairing to assess the accuracy of our surrogate model. And so just as before, we've done this for both the collapse assessment and the non-collapse engineering demand parameter assessment. So for our collapse prediction, our PLoM surrogate model is predicting the collapse at a given structure and site quite well compared to the validation data. And so we can see this in this plot here. The yellow line here is showing our PLoM prediction for a collapse fragility. The green data is showing our validation data. So this is generated using an OpenSeas model for our collapse fragility. And then finally, the blue is showing the training data. And what you can see here is that the yellow and the green, which represent the prediction and the kind of ground truth, so to speak, match quite well in this case. And so once we have those kind of 2 collapse fragilities, we can also compute the annual collapse rate. So here we can combine these fragilities with this gray hazard curve. So a site-specific hazard curve shown on this plot to compute annual collapse rate. And so what we see across these different sites and bridge pairings is that our annual collapse rate from our validation data, which is from our OpenSeas models, is matching our PLoM prediction very well. And so what this means is that we're overall seeing good performance of the PLoM model in this case. When we move to engineering demand parameter prediction, it gets a bit more complicated because instead of a single output, we have 6 different outputs. And so here we can look at, again, this plot is somewhat similar to the one I showed before, with our yellow data being our PLoM prediction, the green being the validation data or our sort of ground truth, and the blue being our training data. And so again, in an ideal setting, this solid green line and the solid yellow line are going to match very well. We're evaluating this in the case of these engineering demand parameters using a KS test, which is a statistical test to determine if 2 samples were drawn from the same distribution. And so these green dotted lines represent the bounds of this KS test that we're using to determine if a certain case is a pass or a fail. And so if this yellow line falls within the green dotted lines, we're calling this a pass case. On the other hand, if the yellow line, our PLoM prediction, falls outside of the green dotted lines, we're calling this a fail case. And so we basically conducted this pass-fail test for our 3 different bridges at 3 different sites with the 6 intensity levels per site and then 2 engineering demand parameters. And so this test is really based on this distance, the maximum distance between the empirical cumulative distribution functions of the PLoM data and the validation data. And so when we plot these for all of our bridges, sites, intensity levels, et cetera, we can create these plots that show overall really strong PLoM performance. And so this green band across the middle is representative of that KS test bounds, with the red kind of error metric shown there accordingly. And so what we see is that across 216 separate evaluations, we're seeing really good PLoM performance with 94% passing this test. And so overall, both in collapse and non-collapse, we're seeing the PLoM model is able to pick up the response of a high fidelity model quite well. And we're able to match kind of what OpenSeas can provide with what this surrogate model can provide. And so moving on, just for the last section of this talk, I'm going to give a short tutorial on using surrogate models in quoFEM. And here again, I'm going to talk about this in the context of this bridge study, but this could be used for other analysis or other structures. And so nothing in quoFEM is kind of specific to this bridge project. Before I get into this, just want to give a brief intro. quoFEM is a SimCenter tool that's called Quantified Uncertainty with Optimization for the Finite Element Method. And in terms of surrogate modeling, this tool has capacity for both Gaussian process modeling and probabilistic learning on manifolds. Again, I'm going to focus on the PLoM model because that's kind of the focus of today's talk. I want to acknowledge the work of 2 people before I jump into this. First of all, Dr. Quanqi Zhang, who is really behind a lot of the PLoM method development for the case of earthquake engineering and worked on a lot of the backend code for quoFEM. And second, Dr. Sangri Yi, who did a lot of the front-end implementation for PLoM in quoFEM and has worked a lot on this. I also want to briefly mention that all of this data is up on the Design Safe Data Depot if anyone's interested as well. And so here we're looking at the quoFEM user interface. And so if you select surrogate modeling, you can see that there are these two options here for Gaussian process modeling and PLoM, which I will focus on today. And so once you select a surrogate model, you can import data. So this is the case where we've run our finite element simulation outside of quoFEM. And so in the case of the bridges, we were running OpenSeas outside of quoFEM, and then this allows us to import our data file into quoFEM for use. There are other ways to go about this, but we found this was best suited for our use case. So once I select that, I can import my input and output data. So here, our input points are just a CSV containing the structural parameters and the ground motion parameters that we talked about earlier. And our outputs are just the structural response quantities, also in the form of a CSV. And once you import these into quoFEM, you can go ahead and select this advanced options checkbox, which allows for a lot of the customization that we can use that I've kind of talked about earlier. And so the first step in this is to assess these hyperparameters. And so kind of initially, as a default, quoFEM has constant hyperparameters. So these values are shown here. So these don't depend on any input variables. These are just constant parameters that we can use for the PLoM model. However, if you recall from earlier, this is actually not what we were doing in the context of the bridges. We have these kind of functional forms of hyperparameters that map from earthquake intensity to our appropriate parameter. And so there's kind of functionality in quoFEM to use this as well. And so if you, again, hit this customize checkbox, you can import Python functions that represent the functional form of this mapping from earthquake intensity up to hyperparameter. In the context of the bridge, these functions are available, but if you were to bring your own, I guess, case here, you could also import different Python functions if you wanted a different functional form for your hyperparameters. The final step is to add this constraint file. And so basically in this third tab, we have a constraint file that basically informs quoFEM what our target is for the surrogate prediction. So this really gets at what bridge are we trying to make a prediction for? What ground motion parameters are we trying to make a prediction for? And so this is really providing all of that information to quoFEM. So once you actually hit run, this will be the output that you see. And if you save this table, you've successfully created a structure-specific, site-specific prediction of these correlated engineering demand parameters using the PLoM model. And so this can be used for a few different things. I think two immediate use cases are sensitivity studies in which you could really assess the sensitivity of our outputs to changes in the input variables. For example, what happens to our engineering demand parameters if we increase the duration of the earthquake, et cetera. And then a second use case is regional level analysis, which is the current direction of this project that I've talked about. But I think beyond that, there are a lot of use cases that could potentially involve the PLoM model. And with that, that concludes my presentation, and I'm happy to answer any questions. Thank you all for listening.
Thank you so much, Mia. It was excellent presentation as always. So we have some questions, but I also want to remind attendees that you can send me the questions so that I can relate to Mia. So the first one is the regional simulation computationally feasible if you use the PLoM model? How much faster than OpenSea's analysis is this model?
Yeah, thank you so much for that question. So I think the short answer to this is yes. And so once we have a trained PLoM model, we can have a computationally feasible regional analysis. So once the model is trained, the computation time for a PLoM model is about 0.4% of OpenSea's analysis. So it is a lot faster. But that being said, I don't think surrogates are necessarily like applicable in every single case. So once it's trained, it's a lot faster, but there's a lot that actually goes into that training process. So in order to train the PLoM model, we ran a lot of OpenSea's models to generate that training data, which is certainly a computational burden. And so once you have a trained model, this allows for a lot of flexibility and use. But there's definitely overhead kind of beforehand to set up a well-trained surrogate.
Right. The second question is Regarding the selection of ground motions, did you utilize only real earthquake motions from California, or did you include events from other parts of the world, or even synthetic ground motions?
Yeah, that's a good question. So we did not include any synthetic ground motions. So these are all recorded ground motions. But if I'm remembering correctly, we did not constrain specifically to California ground motions. The way these ground motions were set up were basically to be reflective of the space we're expecting for California. So given the spectral shape in terms of SA ratio and then the duration, we want all of these to be realistic in terms of those parameters that we're expecting for California. And there's more extensive information on that ground motion selection in a paper that I'm happy to share with whoever asked that question. So no synthetic ground motions were used. These are all recorded, but not constrained to California. I think it could be an interesting direction in the future to use synthetic ground motions because I think you have a lot more control over what your ground motion parameters can be. And so by using real ground motions and just sampling things like SA ratio, and duration, we're losing information there. We're not using the entire ground motion time history for our predictions. And so that's definitely causing uncertainty in our models. So if you do have these really specific recorded ground motions, you can get a lot more information kind of extracted out of that and a lot more control, which could lend itself really well to surrogate model development.
Hi. And the next question is kind of relevant to the question that you just answered.
Mm-hmm.
So I'm curious about the model generalizability.
Yeah.
How would the trained PLoM model be generalized to regions outside of the Bay Area?
Yeah, so that's a great question. So we're the kind of regional test bed that we're using is the Bay Area, but we've set this up to be reflective across California. And so like I just mentioned, the ground motions we're hoping that are somewhat comprehensive in terms of coverage of ground motions in California. And our bridge models were sampled to be reflective of the Caltrans bridge stock. So there was work by a previous PhD student to look into kind of different parameters different expected parameters in different Caltrans bridges. And so these are realistic bridges for how Caltrans is designing these in the state of California. And so in order to generalize outside of the Bay Area, it's certainly able to do that, this model that we've set up. However, because we've kind of set up both the structure and the ground motion parameters in terms of California, I would not recommend using this outside of California because we did not look into how reflective of these bridge parameters were of a bridge in, say, Oregon. And certainly in our ground motion suite, we don't have any of these really large M9 ground motions that you might see in the Pacific Northwest. And so definitely there are some constraints on the generalizability just because we've constrained this to California. But outside of the Bay Area, there is definitely flexibility. So if you were to do a study in a different part of California.
Okay, I got a message from the previous person who posed this question, the previous question. So I recommend you guys to follow up after the recorded portion.
Okay.
And there are some more questions. One is, what workflow, for example, tools or compute facilities did you use to generate the training data? So you said you generated samples outside of quoFEM. So I think that's the question.
Yeah, that's a great question. So this can look different for different people. What we did in this case, it was, I guess, a two-part answer to this. First, in order to generate the training data, we set up this concrete bridge modeler that kind of automatically generates a suite of OpenSeas models with different bridge parameters based on distributions of bridge kind of structural characteristics. And so we were able to kind of automatically generate a suite of OpenSeas models using this concrete bridge modeler. In terms of actually running all of the ground motion time histories through these models, we were able to use the Stanford computing cluster, which is called Sherlock. And so we ran that kind of locally to Stanford on the HPC resources here. But you could obviously do that somewhere else. And I know Sangri probably knows a lot more about this than I do, but there is capability in quoFEM to run these simulations directly and actually do the entire kind of training data generation and then surrogate model development all within that framework. But we ran this kind of separately using the resources at Stanford.
Okay, thank you. I guess the next question can be, what are the main outcomes of the comparison study between different surrogate models, GP, PLoM, and linear regression?
Great, thanks for that question. I think, so this is a kind of a nuanced outcome. There isn't kind of a resounding like one beats the other, et cetera, because these are all really powerful models. I think what we found is that because of the kind of complexity of the hyperparameters in PLoM, there's definitely a lot of, you have to be careful in the way you train this PLoM model in order for it to be accurate. And so if you do put in that overhead and figure out how to properly kind of tune these hyperparameters, the PLoM model can actually be the most accurate across the three because of its flexibility and the way it's set up. However, it is pretty high effort to develop it in the right way. The Gaussian process model, on the other hand, because of quoFEM, honestly, is quite easy to use. And so Sangri has actually set this up really well. And I was able to train my Gaussian process models all the way in quoFEM. And it provides really robust performance with, I guess, a lot less individual effort than creating these hyperparameters functions for PLoM. And so you do get a little bit more accuracy if you use the PLoM model, is what we're finding in our case, but it is definitely like a little bit of a step up in terms of effort. And so both are certainly able to be used in the context of regional analysis, and we're actually currently kind of carrying both through that regional study right now. In terms of linear regression, that's obviously the easiest one to set up and train, but it does provide a lot less flexibility than what we're getting out of GP and the PLoM model. And so I don't want to give either one kind of a absolutely this one or absolutely the other one, because I think they both bring different kind of characteristics to the table.
Okay, thank you. We have a few more questions, but so for the recorded version, I will give you the last question. So going back to the original motivation of the research, I'm wondering if you have any future research plans to deliver somehow remediated details about the hazard responses from bridge structures for regional analysis.
In terms of the original motivation?
Yes, I think the question is referring things about like more detailed structural information, like retrofitted information, or
yeah, that's a great question. So I think the end goal of this study is to have that really detailed understanding of expected bridge performance. And I mean, it's shown on this slide right here, actually. The original kind of funding for this project came from the Peer Center Transportation Research Program and was partially funded through Caltrans. And so I think the ultimate end goal would be to provide a tool that can give really like flexible ways to compute bridge damage and expected performance that could be used by an organization like Caltrans. It's definitely still in the development phase. We're currently trying to build out this regional analysis workflow right now. But ideally, in the end, this would be an incredibly easy to use, hopefully, tool that can be used by practitioners to understand seismic risk in a bridge stock like the Caltrans bridge stock. I hope that answers what that question was intended to be.
I believe it did. Thank you so much. Yeah.
Cool.
So with that, I'd like to conclude live sessions. To our attendees, thank you so much for joining live. I want to remind you that you can register to our live events on our webpage, which is simcenter.designsave-ci.org. So yeah, can you move on to maybe next slide? So we have a SimCenter discussion webpage where we communicate with users, especially when you have feature requests or bug reports. Please feel free to post here and we will be able to respond to you in a short amount of time. And I think there are two SimCenter events coming up. First is Community Roundtable, We will talk about high fidelity modeling of wave-induced forces and structural response. And there's NHERI computational symposium coming up, which is really exciting. With that, this concludes the recorded portion of today's live expert tips with the NHERI SimCenter. We hope you've been inspired by Mia's presentation today and see opportunities for adapting and expanding the capabilities to your research. Thank you so much for joining. Thank you again, Mia.
Thank you.